Hi, Will from Fologram here. In this tutorial, we're going to explain in a little more depth the Grasshopper transform object, which is essentially a 4x4 matrix which is used for moving, rotating, and scaling geometry in Rhino and Grasshopper. You probably haven't come across matrices before unless you've done a little bit of maths. But you definitely would have used matrices in everyday CAD modeling and had them just hidden beneath the layer of the modeling environment that you're working in. With Fologram, we output the position, rotation, and scale of sensor events, like where you might be clicking within the mixed reality environment, or tapping, sorry, where your headset is within the mixed reality environment, where your hand is, where you're dragging. All of these things are outputted as transform objects or 4x4 matrices, and it's important to understand a little bit about how matrices work in order to really easily work with this data in Grasshopper. So to jump straight in, I'm going to explain a little bit about how matrices work, and I'm going to heavily reference what is a pretty fantastic resource for designers or computational designers, which is the Essential Mathematics for Computational Design PDF book by Raja Issa. It's a really good learning resource for understanding matrices, transformations, vectors, common NURBS data types, and you should have a look at it if you haven't already. Okay, so to explain what matrices are and how they work, we're going to just use the standard Grasshopper transform components and break apart the transform objects into their matrix representations in order to illustrate some of the properties of these matrices. So to begin with, let's have a look at how the move transform works. So the move component in Grasshopper, if you've ever used Grasshopper before, you've probably used this component. I'm just going to create an XY plane as something to move, and I'm going to create a vector and set the values of this vector in Rhino in order to move my plane. So here we have it, it's a moved plane, everything's performing as expected. Now there's two outputs to the move component, the translated geometry, which is our plane moved over here, and the transformation data, which is this 4x4 matrix, which represents that translation. We can have a look at that 4x4 matrix using the transform matrix component. Maybe the display matrix component works as well. Okay, they're pretty similar. The transform matrix just gives you an output so that you can continue using this data. This is just a preview. So this is the matrix representation of that translation, the moving of this bit of geometry, in this case a plane, from the origin where it was originally to where it is after it's been translated with this vector. So let's have a look at the vector as a coordinate representation. So this is the x, y, and z components of our vector. I've moved it 131 units in the x-axis, negative 154 units-ish in the y-axis, and nothing in the z-axis. And you might start to see some similarities here between the matrix representation of that translation and the components of the vector. Essentially, to represent a translation using matrix representations, in the final column of our 4x4 matrix, the first three rows represent the x, y, and z translation values of our translation. The way that this actually works mathematically is really neatly explained by Raja Issa, or you can go and look it up in any of the many resources for understanding how matrices work. Okay, so the final column of our 4x4 matrix is representing translation values. So the numbers that you see here in the first three rows are the x, y, and z translation values. Now let's have a quick look at how scale works in matrix representation. So again, I'm going to take my plane, scale it around the origin with a factor of a half. You've probably all used the scale tool before. Here's the outputted scale geometry because I'm scaling a plane. That's pretty unexciting, nothing happens. But we can also get that, exactly like the move, we can get that transformation data as a matrix. Now again, you might start to notice a bit of a pattern here. This kind of diagonal through our matrix, 0.5, 0.5, 0.5, represents the scale factor for each component of the thing that is being transformed. In this case, we transform points. So first column and row will be the transformation of the scale of the x coordinate, the point being transformed, ditto for the y, ditto for the z. Okay, so the diagonal through our matrix, that's capturing scale factors, essentially. Once again, if you want to understand how the maths works, go look it up in many resources which are available. Okay, quickly, let's have a look at rotation. So again, I'm going to grab my plane, rotate 3D. I'm just going to rotate it 180 degrees. I think that's what the default is, yep. Around the origin, and let's rotate it around the z-axis. So we get our rotated geometry as normal in Grasshopper, and if we have a look at the matrix representation of that transform, this one is a little bit harder to pick the pattern, very clearly explained in Essential Mathematics for Computational Design. Essentially what's going on here is when we do a rotation around the z-axis, the matrix representation of that transformation, the first four values, first row, first column, second column, first row, first column, second row, second column, second row. These four represent the, I guess, the trigonometry of that rotation of the point around the z-axis. We can really sort of figure out how that works by diagramming out the trig, the vector maths, which is quite elegantly done in Essential Mathematics here, and also explained in terms of how the rotation matrix represents rotations around other axes. Okay, so this object, the 4x4 transform matrix, is called a transform in Grasshopper. It's given a name, it's called a transform, and there's a specific component called a transform component, which will apply that matrix transformation to an object that can be transformed. So if we, for instance, take this transform data out of, let's say, our move component, and then transform plane, it's going to apply this transformation to our plane, and it'll behave in exactly the same way. We're going to move the object using that matrix transform, which essentially represents the vector translation in this case. Now, with Fologram, if, for instance, we look at the track clicks component, a lot of the output data of the track clicks component is represented as a transform. So I'm just going to connect up my headset. Okay, so I've got my headset connected. I have the track clicks component down here in Grasshopper, and I'm just going to tap somewhere in the physical space so that this component updates. And it's outputted a transform object for the cursor position at the time of the click, and also the hand position at the time of the click. We can also get the device name and a few other things which I'll explain in a later tutorial when we look at the tracks click component in a bit more depth. But it's really important to understand that what the tracks click or track clicks transforms are representing are the position of, in this case, the cursor at the time of the click, the rotation of the cursor at the time of the click, because that is essentially able to model the orientation of where we are when we tap on something, and also the scale. So because you're able to scale the entire mixed reality experience all at once, it's pretty useful to have that as transform data for manipulating your Grasshopper model. So this transform matrix is capturing position, rotation, and scale of our cursor when we tap somewhere in our mixed reality model. Now we can understand that these values here represent the translation of the cursor, where it actually is in space. These values represent the scale, which seems a little bit strange. It's not 1, 1, 1, 1, 1, though actually I can explain how that works in a second. And these values also represent the rotation of our cursor plane at the time of the click. If we look at our hand position when we click, you can see my hand position is moving around while I'm clicking, as well as the rotation is changing a little bit to model essentially the orientation of my hand during the click. So in exactly the same way that we can use the transform component to transform a point and use the transform which comes out of one of these other Grasshopper components like moving, scaling, or rotating, we can use the transform from the Fologram components, for instance where the cursor is, to transform a plane to wherever we click. So now as I click around, I'm going to hide all this other stuff so you can see it a little more clearly. We're going to see this plane move. As the track clicks component updates, as this matrix updates, and then as our component is transformed using that matrix information.